Welcome back to The Explainer. Today, we're looking up at the sky and unpacking something that honestly seems almost like magic, but it's actually a total masterpiece of physics. We're going to break down the exact mechanics of how an aircraft stays perfectly steady in the air, using our source material to really guide us through the visuals. I'm incredibly excited to share this with you all today because I promise, once you actually see the invisible forces at play here, your next window seat on a flight, it's literally never going to be the same. Okay, let's dive right into this. So, have you ever looked out of a plane window mid-flight and just felt like you were hovering? It feels completely static, right? Kind of like the plane is just resting on this giant cushion of air doing absolutely nothing. Well, that perception couldn't be farther from the truth. Cruising is absolutely not a state of doing nothing. It is, in fact, a highly demanding, constant physical battle. Just take a look at this Cessna cruising majestically, perfectly straight and level right over the water. I mean, it looks so peaceful, right? But to actually achieve this unbelievably smooth flight, the aircraft is in a highly active state of perfect physical equilibrium. The airplane is quite literally flying itself through this constant invisible struggle. To really understand this struggle, we first need to define what it is we're actually looking at. What exactly is straight and level flight? Well, in aviation terms, straight simply means you're maintaining a constant direction, or heading, and you achieve this by keeping the wings completely level. Level, on the other hand, means maintaining a perfectly constant altitude. You aren't climbing and you aren't descending. You're just holding your place in the sky. So, who are the invisible combatants making all this happen? Let me introduce you to the four gladiators of physics that are just constantly pulling and pushing at the aircraft. We've got lift pulling up, weight dragging down, thrust pushing forward, and drag holding everything back. Now notice the arrows in this diagram. It is literally an invisible four-way tug of war. The upward force of lift must exactly balance the downward pull of weight. And at the exact same time, the forward thrust, which is generated by the engine or propeller, has to perfectly cancel out the backward resistance of drag. When these opposing pairs lock into this continuous struggle and perfectly match each other, well, aviation physics dictates a pretty simple rule. It tells us that in stabilized, straight and level flight, the airplane is in equilibrium, with no tendency to accelerate or to change attitude or direction. It's basically a stalemate. And that exact stalemate is what gives us that smooth, comfortable ride. But maintaining this forward momentum isn't free. Our source actually uses a fantastic analogy here. They call it the bicycle problem. So think about riding a bike really, really fast into a strong headwind. You feel that heavy air resistance pushing right against your chest, right? Well, that is called parasite drag. Pushing the actual physical body of an airplane forward through the atmosphere creates this exact same type of friction and resistance. Because of this, the thrust from the engine has a massive job. It doesn't just have to overcome that bicycle-like parasite drag. Oh no, it also has to overcome something called induced drag. And induced drag is, literally, a byproduct of the wings creating lift. So the harder the wings work to keep the plane up, the more induced drag they create holding the plane back. Thrust has to battle both of these resistances simultaneously just to keep the plane moving at a steady speed. Now, what's really interesting here is this fascinating dynamic seesaw relationship between airspeed and what's known as the angle of attack. And the angle of attack is simply the angle at which the wing strikes the air. Take a look at the left side of the diagram here. At a low airspeed, the plane needs a very large angle of attack, meaning the nose is pointed high up, just to generate enough lift to counteract its weight. But then look on the right side. At a high airspeed, the plane only needs a very small angle of attack to generate that exact same amount of lift. And because of this dynamic, we arrive at a real golden rule of aviation physics. If your speed drops, your lift drops. It's just direct cause and effect. So to save that lift and, prevent the airplane from just falling out of the sky, the pilot must raise the nose to a higher angle of attack. Basically, the wing has to bite into the air at a much sharper angle to compensate for that lack of speed. So let's actually step right into the cockpit for a second. How does a pilot actually know if they have the right angle of attack? Well, honestly, they look out the window. The pilot establishes a visual relationship between the natural horizon outside and the dashboard or the instrument glare shield inside. If you check out the center image here, that correct nose attitude holds the altitude perfectly. If the nose goes way too high above the horizon, the plane climbs, and if it drops too low, it descends. All of this culminates in a core aviation formula from the text that dictates literally everything we're talking about today. And that is power plus attitude equals performance. It's that simple. If you set your engine power and you establish that correct nose attitude relative to the horizon, you maintain that perfect straight and level equilibrium. It really is a precise mathematical and physical recipe. But of course, altitude isn't the whole story, right? We also have to fly straight, and keeping a constant direction requires actual physical balance. Just look at the slip indicator instrument shown here. Specifically, pay attention to that little black ball in the curve's tube. If the airplane is slipping sideways, that ball just won't be centered. To fix it, the pilot uses the rudder pedals. So if the ball is hanging out to the left, they press the left rudder. If it's to the right, they press the right rudder. It literally steps the plane right back into the center of its airflow. So what happens if you just ignore that little ball? Well, you end up flying uncoordinated with what the text calls crossed controls. Now, you can technically fly straight with one wing dipped down and the rudder pushing the opposite way to keep you from turning. But just look at the diagram. You're essentially sliding the airplane sideways through the air. And doing this completely ruins your equilibrium, it creates massive amounts of unnecessary drag, and it's going to burn right through your fuel rapidly. It is the exact opposite of efficiency. Let's move to the next concept and see how this builds when a pilot actually wants to change their speed without breaking that perfect equilibrium. Let's say you want to speed up, but you gotta stay perfectly level. First things first, you increase engine power. The plane speeds up, which naturally creates more lift, so the nose immediately wants to rise. Second, to stop from climbing, the pilot must manually lower the nose to decrease the angle of attack. And finally, they have to retrim the airplane for this brand new speed. So the really crucial point here is this concept of trim. You see, constantly holding forward or backward pressure on the control column just to maintain an attitude, that gets exhausting fast. I mean, nobody wants a crazy arm workout for a 5-hour flight, right? Well, trim tabs are these small aerodynamic surfaces that the pilot adjusts to relieve those heavy control pressures. Once that new equilibrium of power and attitude is perfectly found, the pilot adjusts the trim, essentially locking the airplane into that state so it flies itself completely force-free. We've seen today just how beautifully complex it is just to fly in a straight line at a constant altitude. It requires thrust exactly matching drag and lift exactly matching weight. But I want to leave you with a provocative thought based on everything we've uncovered today. If straight and level flight requires this incredibly precise, super delicate equilibrium of 4 massive physical forces, what do you think happens to that harmony the exact second the pilot decides to turn the steering yoke? Think about it. Until next time, keep looking up.